Well, now you have a proper understanding about the basic mathematical relationship between symmetrical and asymmetrical components, okay? Something that you must realize is that symmetrical components are similar to the per unit system. I mean, per unit system work perfectly and make your life easy and is a very important tool for power system analysis. But the per unit system, they must follow and obey all the basic rules of electrical engineering. Three-phase configurations, power, Ohm's law, Kirchhoff law, and so on. The same happens with symmetrical components. In this case, I would like to introduce the very basic property of symmetrical components applied to power, okay? If we are working in an electrical power system and there is an unbalanced condition, okay? Let's say voltages are unbalanced and currents are unbalanced. To be honest, the basic properties still working. The total power in this three-phase system, unbalanced system, will be the power that is on phase A plus B plus C. That is basically a property that it's working for unbalanced system or for balanced systems, okay? What we want to do now is, what's happen if we apply symmetrical components? Well, let's do it, okay? In this case, you can see we will do a very important trick here, okay? What we want to do is first, we want to convert this equation here from this linear form into a matrix or vector form, okay? What we can say is here we have the product between voltage and the conjugate of current, three times, one for phase A, one for phase B, and one for phase C, okay? We can use vectors and we can say this is the vector voltages vector, this is the asymmetrical voltage vector, and this is the asymmetrical voltage for currents. Of course, there is a conjugate here that is coming from the definition, okay? Then we can do something quite interesting. What's happened if we say, okay, let's simplify this equation, and now instead of using this vector in this way, we use the transpose. Well, there is no problem. There is no problem using the transpose vector. There is not any change on the mathematical properties, but look much better and it's making things simple, okay? What we will do now is we are saying that the three-phase power is the asymmetrical vector, voltage vector, transpose, multiplied by the conjugate of the asymmetrical currents, okay? Then we use the two properties, two identities that we showed before, the relationship between asymmetrical and symmetrical components using the matrix A, okay? Well, very simple. What we are doing here, let me use here the pen, okay? What we are doing is, let's put here this one, and let's put this one there, okay? When we put this here and the voltage is there, we obtain this beautiful and interesting matrix over there, okay? To be honest, those elements here, the voltage and the current, there is no problem. I will focus my discussion right now on what is the transpose of the matrix A multiplied by the matrix A. I will focus my discussion over there because it's extremely relevant, okay? Let's move to the next slide, okay? I will not run the full demonstration here, but I need that my student understand I need that my students understand that this product here is the key, and the transpose of the matrix A is the same matrix A. And the inverse of the matrix A is 1/3 of the conjugate. Remember, this symbol here is the conjugate. Is the conjugate, a third of the conjugate of the matrix A. Then, when we create the product, remember we are interested in this product. When we run the mathematical operation, wow, beautiful. This product means 3 times the identity matrix. That means 3 here, 3 here, 3 here at the identity matrix. And when we put those numbers together, look over here. The beautiful equation number 9. The equation number 9 say that the three-phase power can be calculated like 3 times the product of the symmetrical components of voltages multiplied by the symmetrical components of currents, considering the conjugate. That is beautiful. What I'm trying to say is this is 3 times the power dissipated at zero sequence. This is 3 times the power dissipated at positive, and this one is at negative. This is a very important property, okay? The next step that I will do now is we need to discuss what's happened if we have a symmetrical impedance in our power system. Symmetrical components, they are a beautiful tool, and they can be used especially if we have any kind of asymmetrical behavior. And one of those asymmetrical behavior is related with open faults, a single phase open or 2 lines open, okay? Now, I believe you can see here we have a 3-phase. Let's say this is a 3-phase line, and we have asymmetrical impedance over there, okay? You can see that set A, set B, and set C, they are the impedance located in the line A, line B, and line C. You can see here this impedance for phase A, for phase B, and for phase C. Okay, good. Now, what we need to know is we can still using Ohm's law. Ohm's law is valid for symmetrical and asymmetrical condition, for balanced and unbalanced condition, okay? Ohm's law say that the voltage drop here in this series, in the line A, the voltage drop will be the product between between current and on the line, and the impedance is the same for the line B and for the line C, okay? Good. Now, what we need to do is create a matrix representation. The voltage drop on the series on line A, B, and C is the product between impedance and the current. And then what we need to do is, okay, we can write here the symmetrical components, 0, positive, negative sequence for those voltages, and then 0, positive, and negative sequence for the phase current on line A, okay? Then what we need to do is something quite simple. If we multiply by the inverse of matrix A, if we multiply by the inverse of matrix A, well, we can define here at the very beginning of this expression something that is extremely helpful, okay? This is what we call the sequence impedance. If we have symmetrical components, they follow the Ohm's law. That means that symmetrical voltage should be equal to the symmetrical or sequence impedance multiplied by the sequence currents. Okay. Well, the next step is, okay, what's happened if we have the same impedance? If the impedance on phase A and phase B and phase C, if they are the same, well, we can say that the voltage drop in each sequence is the impedance multiplied by the corresponding sequence currents. That is the conclusion here. What I'm trying to say is, in positive sequence, the positive sequence current is the only one creating voltage drop. Okay, good. Let me complicate a bit more the problem now. Let's think about a three-phase transmission line, but in this case we are considering a bit more complex situation. I believe all of you can see on the left-hand side, this is the situation of a three-phase line, but there are some self-impedance phase line A, line B, and line C. And then we have some mutual coupling that is represented by mutual reactance. Okay, in this case, we have here set AC, set AB, and set BC. Now the situation is a bit more complicated because the line current C is affecting the phase A, but also the line current B because the mutual coupling is affecting also the phase A. What I'm trying to say is the voltage drop across the segment here is defined by the self-impedance set AA and the current moving on the line A plus the mutual voltages created by current B and current C. We can do the same for the other two lines, and at the end we can create a matrix form like over there. What we need to understand is that typically in a transmission line, when we have mutual coupling, there are some properties that they are quite typical. The property is that between A, B, and C, the self impedance is the same for the line A, B, and C. The reason is quite simple. The conductor is the same, and as consequence, the magnetic influence over the conductor by the line current, they are the same. As a consequence, we can call this one set P, okay? Uh, the impedance, it's typically the series impedance, the self impedance is typically the same at each line. And for line A, B, and C, we have the same series impedance, and the mutual impedance, we assume that the effects are symmetrical. I mean, the effect from I to J is the same effect from J to I, and we call that the mutual impedance, okay? If that is the case, um, this matrix present here, that is a 3 by 3 matrix, it can be simplified in terms of the main diagonal with the series impedance here and the mutual impedance out the diagonal, okay? But coming back to my explanation, using the symmetrical components, we can obtain that the sequence matrix for the transmission line, and that means that this will be the zero, this will be the zero impedance for the transmission line. This will be the zero impedance for the transmission line, and this will be the positive sequence, and this will be the negative sequence for the transmission lines. Okay, sorry about my ugly handwriting, but what I'm trying to say is in this case, this is zero, this is positive, and this is negative sequence impedance for the transmission line when we consider a symmetrical effect between the mutual impedances, and we consider that we have the same series impedance at each line. Okay. In very basic way, you can find here the same expression defining the positive, negative, and zero sequence impedance of the transmission line. What I'm trying to say is the power system, each one of the components inside the power system, they are basically symmetrical elements, okay? The power system, as I say before, for economical reason, is a three-phase system, but because design, the power system is a symmetrical system. And what does mean that the power system is fully symmetrical? Okay, that means that we have the same series impedance in any component, that the effects in the mutual impedance are equal, that we are using rotating machines, that they are symmetrical from the old point of view, and also we are using symmetrical transformers. The only elements that introduce some asymmetrical aspects in the power systems are the transmission lines. However, there is an assumption that if we transpose the transmission lines, we are balancing the asymmetrical effects, and at the end, the power system can be, we can say that the asymmetries, the imbalance inside the power system are negligible. Okay. But if we have an asymmetrical fault, like a single line to ground or a line to line short circuits, that is a very dangerous situation, and that is an unbalanced situation that require the use of the symmetrical components. And what I want to say, and this is very important for all of you, is that you must understand that every single device have a impedance. We use impedances to represent the behavior of any element inside the power system. Any device will have positive sequence impedance, will have a negative sequence impedance, and a zero sequence impedance. What I'm trying to say is every single component inside the power system, they must have impedances representing the behavior of the component to each one of the possible sequences, positive, negative, and zero sequence, okay? As I say before, transmission lines, they are the only devices that they introduce asymmetrical conditions. It's probably one of the few components inside the power system that where positive and negative sequence can be different, but in many cases, in many devices, positive and negative sequence are typically the same. Where we can identify a very big difference is between this positive and zero sequence, okay? Typically, the zero sequence can be a very different value compared with the zero sequence. In a minute, we will talk about different components and different elements, okay? But another concept that I need my students to understand is the concept of sequence networks, okay? I say to you that every single device have a model, and this model is representing the behavior of the component at positive sequence, negative sequence, and zero sequence, okay? If there are several impedance, because there are several components, as a consequence, we will have different networks. To be honest, we have what we call the sequence network. The sequence network corresponds to the use and a single phase equivalent model for each sequence. Okay. To be honest, what we have done with the symmetrical component with the symmetrical faults using the Thevenin theorem is using only the positive sequence. Right now, because we are studying asymmetrical faults and we introduce the concept of symmetrical components, right now you must understand that when we are analyzing asymmetrical faults, we need to use the concept of sequence network, and they corresponds to the equivalent phase circuit that we create by the impedance in a very specific sequence. The sequence networks, they can have some sources. But all my students, they must understand that the sources must be only present at the positive sequence. What is the reason? Because the only devices creating voltages inside the power systems are the synchronous generators. And those synchronous generators, they are designed in order to create only positive sequence voltage. For that reason, all my students must realize that the positive sequence is the only sequence network that you can find voltage sources, okay? If we move forward, I would like to start from the very basic concepts, and I would like to tell you that the synchronous machine, I will start my discussion about sequence network starting from the basic concept of the synchronous generator, okay? Let's consider the following. Imagine that we have a classical three-phase synchronous generator, and this synchronous generator is rotating at nominal speed. The excitation is such that the terminal voltage is the nominal, and we have a star-connected synchronous generator. You can see here the three-phase diagram, and the neutral point is connected to ground using an impedance, okay? Here we have the current on line A, B, and C, okay? Suddenly, there is a problem. Suddenly, there is a short circuit. And in this case, if the short circuit have contact with ground, as a consequence, the neutral point, if the fault that is happening at the terminals, there is contact with the neutral point and ground, the neutral point will be the return path for the asymmetrical currents, okay? Let's say for a moment that we are assuming that the fault is happening when the line A is connected to ground, okay? I don't know if you realize, but we are closing here a loop, and the fault current that is moving through the line A will return back to the circuit using the ground returned and moving through the neutral point, okay? During the fault conditions, we can say the following. Okay, we can say that in this fault condition, imagine this fault condition, we can say that we have only positive sequence, because in this case the generator is producing positive sequence on phase A, phase B, and phase C. I am talking about sequence voltage generated by this synchronous machine. The synchronous machine is rotating at one direction, and as a consequence, all the voltages are created based on the positive sequence. What is the equivalent? What is the equivalent model or the equivalent circuit for this generator? Well, it's extremely simple. It's the only component where you will find this voltage source, and this is the internal voltage source of the synchronous generator. And using the most basic model, this ideal voltage source is in series with one impedance, and that is the positive impedance of the synchronous generator. You must realize that this model is for positive sequence, and as consequence, this is a line to neutral or a single phase equivalent model. Equation 16 here allow you to identify the relationship between the internal voltage and the terminal voltage on positive sequence based on the positive sequence impedance and the positive sequence current, okay? What is happening on negative sequence? In negative sequence, this machine is not possible to produce voltages. For that reason, if you look here on the right-hand side, the equivalent circuit, there is not any voltage source. I must be totally sure here that you understand that there is not any voltage source in any component in negative sequence. What is the reason? In classical power system, there is no component producing negative sequence. There is no component producing negative sequence. Okay? In this case, the model is just the negative sequence, and that represents the terminal conditions between line to neutral, defining the negative sequence voltage that is caused when the negative sequence the current is moving through the negative impedance. Okay? Here you can see what is the relationship between voltage and current. Probably you are wondering what is the reason for the negative here. Well, you must not, because what we need to consider here is that this is a generator and the current direction is supposed to be going out from the generator. But Ohm's law say that the voltage and current, they are related by the impedance, but the current direction is creating a negative voltage drop. That is the reason for the negative over there. Finally, the most important step. The most important step is the model for negative sequence, for zero sequence. This model is extremely important, and I need that my students understand something very important. Zero sequence means that the current, the zero current here, there, and there, you must remember for properties that those currents, they have the same magnitude and there is not phase angle between them, okay? As a consequence, you must understand something very important. This current here is numerically equal to the zero sequence on the phase A, and this current here is numerically equal to the current of sequence 0 on phase A. If we apply Kirchhoff current law at these nodes, what we realize is that the neutral current is a beautiful property. We have zero sequence here, 1, 2, 3. That means that the neutral point is 3 times the zero sequence. Okay, but what is the important thing here? Well, the important thing here is that we are trying to create an equivalent model for zero sequence. I believe you realize that here there is a voltage drop, and the voltage drop is created by the product between the zero sequence current and the zero sequence current and the zero sequence impedance. This voltage drop here is represented at the equivalent model like this voltage drop over there. Okay, we are clear. But the next point is probably the most interesting one, because the next one must represent the voltage drop across the neutral point between the neutral point and ground, okay? Between the neutral point and ground. And what you need to understand is that in the neutral point, because the components, zero components, they are moving here, 3 times the zero components is moving across this impedance. Now, what we need to understand is the following. The voltage drop here, we can write the voltage drop over there. Let me put here. The voltage drop between the neutral point and ground will be, let's see, the neutral current multiplied by the neutral impedance. That is However, in terms of zero sequence, we have 3 times the zero sequence current multiplied by the neutral impedance, okay? Now, what what we can do to represent the same voltage drop here is, okay, in this case here, we are assuming that there is only one zero current moving in this series circuit. But if we look over here, the voltage drop between the neutral and ground point will be 3 times neutral point zero sequence. What I'm trying to say is that this extremely important number 3 that is present here in the zero sequence neutral impedance is coming to represent the voltage drop, these 3 times here. This number 3 here is used to represent that the neutral current is 3 times the zero sequence in the 3-phase equivalent model, and we represent that voltage drop here using 3 times the neutral point, okay? I need that my students must clearly understand that the connection between the neutral point and the grounding point, they have very important properties on the performance of the power system during asymmetrical conditions. For instance, a very interesting question to my student is what will happen if the neutral point, if we look the neutral point, what's happened if this neutral impedance is there is no connection here. If there is no connection here, this is an open circuit. If we say that there is no connection, this is a number extremely big, this is an open circuit, and the zero component should be equal to 0. Okay? Okay. Now, the next step is we need to talk about what is the sequence network when we are working with 2 winding transformers, okay? With 2 windings forward transformer. As you must remember, when we are working with 3-phase systems, they are basically 2 different 3-phase connection, balanced and symmetrical 3-phase connection. One is the delta and the other one is a star, okay? You must realize that if we are working with 2 winding transformer, there are few combinations. Delta star, star delta, delta delta, star start, and these star, they can have a neutral connection to the grounding point, or they can be floating. What I'm trying to say is there are many combinations, okay? And what I need my students to understand is that all those combinations, they follow a very basic rule, okay? At this moment, I will just focus on zero sequence networks, okay? I will focus only on zero sequence networks, okay? And what you need to understand is in any two winding transformer, you can imagine here with my ugly handwriting, in any two winding transformer, if the zero sequence can move in this side of the transformer, is because it's allowed to move also on the other side of the transformer, okay? That is a basic rule. If we neglect the magnetizing branch, the primary winding current cannot flow, at least the current is moving on the other side, okay? And now what I will do is I will apply this statement in order to determine the sequence network for the two-winding transformer, okay? Let's start with the most basic and very important connection, okay? In a star-star connection where the neutral points on the high and low voltage side, the neutral points are connected to the grounding point, the equivalent sequence network is extremely simple and very simple for my students to see. I believe, let me use here the pointer. I believe you can see this is the high voltage side and this is the low voltage side. Let's assume that we have in an unbalanced condition and there are some zero sequence current here, okay? If they are zero sequence here, they will go to the neutral point and then they can go to ground. That means on this side of the transformer, the neutral point is allowing the circulation of zero sequence. Those zero sequence currents will go to ground and they can go back to the low voltage side of the transformer because the low voltage side have the neutral point connected to the ground. What I'm trying to say is because we have a star-star connection and both sides of the star connection, they are grounded, the ground is the common point where the zero sequence component can move from the high voltage side to the low voltage side. What I'm trying to say is this model is extremely simple because here you will have the high voltage size zero sequence component currents, and here you will have the low voltage current zero sequence components, okay? That is extremely simple to see. The neutral point when it's connected to ground that allow the circulation of zero component, zero sequence component between high and low voltage. But what's happened if we have a transformer, and in this case the transformer is delta connected on the high voltage side, but the star connection is ungrounded, is floating. There is not physical connection between the neutral point on the high voltage side and the grounding point, okay? And on the low voltage side we have a good connection to the grounding point. What I am saying is the star connection, there is no connection neutral to ground. Okay, if that is the case, we have a problem here because in this case, let's assume that there are some zero components, they will arrive to the neutral point and they don't have any point to go to ground. As a consequence, it's impossible that we have zero sequence on the high voltage side. And on the other hand, we have a neutral grounding point here, but because those zero sequence on the high voltage, they cannot go to ground, as a consequence, there is not path for the zero components. For that reason, if you look over here, there is an open circuit, a clear open circuit, because the zero components from the high voltage side, they cannot move, and as consequence, they will never reach the low voltage side. That is the equivalent or the zero sequence model for the transformer. Okay. Now let's go to see the deltas. Wow, delta-delta connection, okay? Delta-delta connection, we can call this DD, where the capital D represent the high voltage side and the lower D represent the low voltage side. What is the situation here, okay? In this case, this model is quite interesting, okay? You will find different models in few books, but all of them will have the same property, okay? The same property is that you cannot have zero components here in the line and you cannot have zero sequence here in the line, okay? What I'm trying to say is when we have delta connections, we don't have possibility of having zero components at the lines because there is no way that the zero components go to ground and then emerge on the other side. And on the other side is the same. We have a delta connection. The delta connection doesn't allow the circulation of zero sequence component. As a consequence, what is the representation in this case? Well, on the high voltage side, the transformer is an open circuit for zero current, zero sequence currents. And on the low voltage side, also the transformer is an open circuit for zero current, components, okay? Something that is must be clarified here, because there is a lack of neutral point. There is no way that we can have zero components on the lines, on the high voltage side and also on the low voltage side, okay? Finally, there is one more case that is quite relevant and quite important for you, okay? And that is the case of the delta star connection, okay? What's happened when we have a delta connection on the high voltage side, and then we have a star connection on the low voltage side. In this case, the neutral point of the, in this case, the neutral point of the well, delta-delta connection, also known as DD, capital D for high voltage side, lower D for low voltage side, okay? Delta-delta connection is a very peculiar connection, and the job right now is to identify what is the zero sequence network, zero sequence model for the delta-delta connected power transformer. I think you can realize that there is interesting thing here, because when you have the delta-delta connection, there is no neutral point. And because there is no neutral point, there is no possibility of having any zero sequence current. That is the reason that when the zero sequence currents arrive here to this node, there is no way that they move they move freely from the high voltage to the low voltage. To represent that situation, this is the line to neutral equivalent model, the zero sequence model. You can see that we have an open circuit here to represent the fact that there is no possible line current, zero sequence line current on the high voltage side. On the other hand, you can see here at the low voltage side also it's happening the same. We don't have any kind of neutral point or connected to ground that allow the circulation of zero sequence components. Okay. One remark that I want to say is that in the delta delta connection, there is no possibility of having zero sequence current here at the line. Yeah, there is impossibility, and that is the reason that we have an open circuit here. And also, it's impossible that we have on the low voltage side, and that is the reason for the open circuit on the other side. Okay. However, what is this representation here? This representation here, what it's trying to do is that zero sequence can be inside the delta connection. I will not go in those details because that is not extremely relevant for the calculations that we will run now, but that is the understanding of that closed loop in the zero sequence model. For zero sequence of the delta delta transformer. Okay. What you need to understand is that there is not possibility of having zero sequence current through the lines connected to the transformer. As a consequence, the equivalent model is an open circuit from the lines in both sides. Okay. Now let's go for a very interesting connection. Now let's talk about the star delta connection. But in this case, we assume that the star connection has the neutral point connected to the ground. Okay. Okay. If you are with me, you can see here. We have here a transformer. In this case, the delta connection is located at the high voltage side. The delta connection is connected at the high voltage side, and we have a start connection on the low voltage side. In this case, the low voltage side, the neutral point is connected to ground, solid connected to ground. Okay. What is the zero sequence model? Okay. Well, the start connection with the neutral point connected to ground, that's allowed the circulation of zero sequence components. Okay. What I'm trying to say is that in this side, in the low voltage side, in the star connected connection, yes, there is possibility of zero sequence currents. Okay. And that is what we are trying to simulate with this circuit here, saying that there is possibility of zero sequence current coming through the neutral point and going back to the line. Okay. However, on the other side, we have here an open circuit. And the reason for the open circuit is clear because the delta connection has no neutral point, and there is no possibility of zero sequence currents going through the lines. To represent that, the zero sequence model, there is an open circuit, and you can see over there that situation. Okay. Okay. Well, there is one more connection. In this case, is a star delta connection, or YD, lower D, because we are using the low voltage. As you can see, we have a transformer in this situation here. We have here a transformer, and this transformer, the high voltage side is connected using a star, and however the neutral point is not connected to ground. Okay. And in this side, in the low voltage side, we have a delta connection. Okay. Now the interesting question is what is the sequence network, the equivalent model for this zero sequence. Okay. Well, it's quite interesting. Here we have the zero sequence, but when they reach the neutral point, there is a problem. Because remember, if we have zero sequence here, they will go to the neutral point, and at the neutral point, they will try to zoom out, but that is impossible because the neutral point is isolated from ground. Okay. That situation is represented here with this open circuit. That open circuit is meaning that, okay, here we cannot have zero sequence, and also on the other side, the delta side have no neutral point, and also it's impossible to have zero sequence component. Coming back to the model, typically we include the zero sequence impedance of the transformer where the start connection is located. We have an open circuit at the lines because there is impossibility of having zero sequence currents moving from one side to the other side in this connection. Okay. Okay. I need that you understand that um, this kind of information must be in your mind how to create the model and how to identify the proper sequence model. Okay. Now the next step is that we need to identify a sequence model for other components, um, is the fact that um, we need to create the sequence model for the balance loads, okay? Well, in this case, we are talking about static loads. When I say static loads, we say that it's any kind of load that can be represented by a simple impedance. Okay. Um, Now we need to define the proper sequence model for the three-phase loads, and in this case we are assuming that we are working with balanced loads. Okay, that means that the impedance at each line it will be the same. Okay. Um, Also remember, when we are working with three-phase loads, they are mainly two basic connections, balanced connections. We are talking about the delta and the star, okay? Well, as I said before, in this case, we are just focusing on static loads that can be represented by impedance. Um, in this case, we are assuming that because they are represented by impedance, they follow the linear rule, okay, the Ohm's law. And as a consequence, we can create a specific model for the sequence when this load is subject of be supplied by asymmetrical conditions. Okay. The first thing that you must realize and you must understand is that static loads, they are represented by impedance. And in that cases, the impedance that we have, ohms, for instance, the impedance is a constant value, and the load is not discriminating, is not identifying sequence positive or negative sequence. Okay. What I'm trying to say is that a classical assumption for static loads is that the positive and negative sequence, they have the same value, and that is the ohms that we specify. Okay. What is the reason for that? Well, if you remember the application of sequence the of sorry symmetrical components, symmetrical components say that the voltage should be equal impedance multiplied by current. That is Ohm's law. But for instance, for positive sequence, the positive sequence voltage will be equal to the impedance multiplied by the positive sequence current. Okay, and and to be honest, what I'm trying to say is that if you apply the voltage in sequence A, B, C, the current will be the same that if you apply A, C, B. Because this is a static load. This is just an impedance. An impedance, they don't care if you apply positive or negative sequence because it's not affecting the load. Okay. In real life, we have another loads, and changing the sequence could be a massive problem. But in this case, what we need to understand is the positive sequence and negative sequence, when we are working with loads, they have the same numerical values. Okay. Where I want to go is about the zero sequence. Okay, zero sequence is very important. In that case, the connection that we are using for the load is extremely important because that define the proper model. Okay, let's start the discussion with a very basic case. In this case, we have a star connected load, but the neutral point you can identify here, the neutral point is not connected to ground. Okay. What is happening now? Well, in this situation, every one of you can understand that there is not possibility of having zero sequence current. Okay, what is the reason? Well, again, if we have a zero sequence current here, let's say this is the zero sequence coming from the line A, when they arrive to the neutral point, remember that we have Kirchhoff current law. When they arrive to the neutral point, there is no way to go in somewhere else. And as consequence, the neutral point is floating or isolated or disconnected from ground, and it's impossible to having any kind of zero sequence. How do we create the model? Well, very simple. The model will be in the lines we will have here an open circuit going from the line to the ground. Okay, this is the grounding point. You can imagine this is the grounding point. You can imagine this is the neutral point, and there is not connection between the neutral point and ground. Okay, as a consequence, it's impossible having zero sequence component in this load. Okay, but this is the case when we have a star connection, a star connected load, a static load, and the neutral point is disconnected from ground. Okay, but let's see what will happen if we now have the same static load represented by impedance, and these impedances, they are connected at the common point, the neutral point. And now the neutral point is connected to ground using an ideal connection, zero impedance. Okay, in this case, yes, we have possibility of zero sequence current moving in this system, and you can identify here zero sequence currents will go from the line, then will add up at the neutral point, then can go down to the ground, and they can circulate inside the power system. You must understand clearly that when we have a solid ground connection on the neutral point, we have possibility of zero sequence currents moving inside the system. Okay, you need to be careful, and you need to care about what is the scheme used for the connection between the neutral point and ground. Okay, now let's move to another interesting connection. In this connection, as you can see over here, as you can see, we have now a neutral point, but in this case, the neutral point is connected to ground using a impedance, and that is the neutral impedance. Okay, what I'm trying to say is, okay, let's think about what should be the path for the zero sequence currents moving on the line A. Well, they arrive here to the line A, they move around, they create a voltage drop on the load impedance, then arrive to the neutral point. And that is where the thing starts to be interesting for my students, okay? Because when the currents arrive to the neutral point, there is a voltage drop. There is a voltage drop over here. And the voltage drop that we have is, we can call that the neutral voltage, and that should be the neutral impedance multiplied by 3 times the zero sequence current. Okay, that is the voltage drop. Okay, but now if we are creating the single phase equivalent model, we need to take in account that voltage drop. And what is the easy way to represent that voltage drop inside the zero sequence model? Well, we know that the current here that is moving across this impedance, the neutral impedance, is the zero sequence current. What we need to do is put here a number 3, and now we will be able to replicate that voltage drop across the neutral point, okay? Something that is extremely important and you must understand, including an impedance between the neutral point and the grounding point, they can provide some advantages and disadvantages, okay? Some advantages because adding impedance at the neutral point, you are adding impedance that can affect the short circuit level, the asymmetrical short circuit level, because you are adding an intentional impedance in the zero sequence model. To be honest, in the zero sequence model will be 3 times the impedance, okay, in the line to ground model. But the important thing here is that you must understand that also because you are adding that impedance, there is a voltage drop and you will have a voltage difference between the neutral and the ground, okay? What I'm trying to say is that if you have an impedance and that impedance is different to 0, it will be a voltage difference between neutral to ground. That means that you can start to have some over voltages in your neutral point, okay? You need to be careful with this. Um, I make a very deep explanation about that in my classes of advanced power system, where the neutral impedance must be calculated in order to improve the performance of the power system. Okay, don't take the impedance connect in the neutral point lightly. Okay, because it's a very interesting and um, very important topic, okay? Because we need to be sure that that impedance is connected over there and making many things at the same time, okay? It's not only used during the fault condition. Finally, here we have a delta connected load, and the delta connected load. The model is extremely simple. I think all my students can see that if we have a delta connected load, there is not possibility of having line currents, okay? Zero sequence line currents. What I'm trying to say is because we don't have neutral point here in the delta, as a consequence, there is not possibility of having a zero sequence currents here, okay? And what is the reason for this loop? Well, this loop is used to represent the possibility of some internal zero sequence moving inside the load, the delta connected load, okay? That discussion is beyond this course. If you want, you can take my advanced module on power system analysis, and then we will discuss the effects of having this zero sequence at delta connection, okay? Well, this has been a very long day, a very long class. We have talked about many things. I would like to close this session with a general summary. In this class, we started talking about and presenting a discussion of asymmetrical faults. Asymmetrical faults require a new mathematical tool. That mathematical tool will make the problem easy to solve. And that is the theory of symmetrical components created by Charles Forster-Q in 1918. Okay, the theory of symmetrical components is used in order to create a transformation between symmetrical variables and asymmetrical variables, okay? We have applied symmetrical component, the theory, in order to define model for three-phase equipment. Basically, we discuss loads, transformers, transmission lines, and generators, okay? And we have applied those those symmetrical components also to power. Okay. Finally, here you will find some references. Again, if you are using a Stevenson book, you will be able to go to chapter number 9 and have a reading. But if you prefer using some other books like Glover, I think Glover is chapter number 8. And no, sorry, yes, it's, chapter number 8 at Glover. Or if you want, you can have a proper reading of the beautiful book of P.M. Anderson, P.M. Anderson, Analysis of Faulted Power System. The first 3 chapters are extremely brilliant for my student at this module, okay? Well, I would like to say thank you to all of you for coming to this important video. And today we were talking about power system analysis, and specifically we covered the topic of symmetrical components and zero sequence network. Thank you very much for watching this video. I hope you will find this useful, and thank you.